Let's go back now to see how we can actually put all of this in practice and calculate gradients using computational graph. So as we saw earlier last week, I believe, training a neural network consists of modifying the network's parameter so as to minimize some loss function on the training set. So in principle, any kind of optimization algorithm could be used. But in reality, almost always we train neural networks using some variation of stochastic gradient descent. And when we discussed logistic regression and simple feed-forward network, we discussed gradient descent, and we said the goal was to minimize a loss function L, which is a function of a vector parameter W, which contains all the parameters of a network. And then each update step in the gradient descent looked exactly the same. We say we just take a step in the opposite direction to the gradient to make sure that we're reducing the loss function. And we had a parameter called alpha, which is the learning rate. And we said this parameter is very important in determining how fast the network learns, and also if it learns in the first place. If the learning rate is too high, then it will never converge. If it's too low, then it will take forever to converge. So for standard gradient descent, then the loss L is defined with respect to the entire training set. Now, we later said that calculating the gradient over the entire set is not optimum because that takes too long for us to do and would only allow us to take a step after we calculated the gradient over all the training set. So we used instead something called stochastic gradient descent, which is defined with respect to a mini batch of size m that's sampled randomly from the entire training set. So we just calculate the gradient with respect to this random sample and then take a step. So there are a lot of enhancements to this basic gradient descent idea that we discussed. So we're not going to have the opportunity to discuss all of them in this class, but some of the most important one you should be aware of. So since for most networks that solve real-world problem, the dimensionality of the parameter vector W and the size of the training set is very large, we always try to use a small mini batch size M, okay? And now hope that the randomness in selecting that mini batch helps the algorithm escape from being stuck in a local minima in a high dimensional weight space. So, and the small mini batch size also ensures that the computational cost of each weight update is small. Okay, it's not, we don't have to evaluate the function over the entire training set. Now, because the gradient contribution of each training example in the stochastic gradient descent mini batch can be computed independently, typically we use GPUs to take maximum advantage of this parallelism, where we're able to just calculate the gradient with respect to each one of the parameters independent. So to improve conversion then, it's usually a good idea to use a learning rate that decreases over time. So you want to start with a large learning rate when you're still discovering the problem and the parameter space. But then as you converge to the optimum, you want to reduce the learning rate so that you don't overshoot it. So typically we choose a schedule, or typically this is one of the most critical components of training machine learning models, is the schedule of reducing the learning rate. So near a local or global minimum of the loss function, the gradients estimated from small mini batches will often have high variance and may point in entirely the wrong direction, making conversion difficult. So one solution then to deal with this problem is to increase the size of the mini batch as you converge. This way you reduce the variance in the direction of the gradient. Another way that's very popular is to use what's called momentum, which keeps a running average of the gradients from past mini batches in order to compensate for small mini batch size. So overall, the process of learning the weights of the network is usually, one of diminishing returns. So we run it until there's no longer practical, usefulness to decrease the test error by running longer. Remember, your goal is to do well on an unseen set of data. So at one point you realize that you're letting the training run much longer, but you're not really improving that much on the test set. So there's no point then to keep training. So this doesn't mean that we reach the global or even the local minimum of the loss function, but instead it just says that, okay, it's not practical to keep going because we're not improving that much. Or we might even make the model perform worse by overfitting the training data. Okay, so keep in mind all of these when you train a neural network model, that the goal is to train the model but not to overfit the training data too much, so that you still do well on out of sample data. Now let's look at computing gradients in computational graph. So before, earlier we saw that the gradient can be calculated using back propagation from the output layer all the way through all the hidden layers. And we also said that this results holds true in general for any feed-forward computational graph. Okay, so let's discuss this in more detail. The backpropagation process then essentially takes information back along each link in the network from the output all the way to the input. At each node, the incoming information is collected, and then we calculate something and then pass it back to the previous layer. Now, this information that we calculate at each layer is essentially all the partial derivatives of the loss function L. For example, the backward message partial L partial Hj is the partial derivative of the loss function L with respect to J's first input, which is the forward message from H to J. So this is a typical partial derivative. Partial L partial H is equal to partial L partial Hj plus partial L partial Hk. So the node H can compute the derivative of L using this equation then with respect to H by using a sum of all the information coming to it from J and K. Now to compute the outgoing message to the previous layer, we are going to use the chain rule like we discussed earlier and say partial L partial FH is partial L partial H times partial H partial FH. The backpropagation process begins with the output nodes, okay, where each initial message is calculated directly from the expression for L, because we already know the exact loss function at the output node. That's where we calculate by comparing the predicted value y hat to the true value y from the training data. Now, at each internal node, the incoming backward message are added together, and the outgoing messages to the previous layers are generated. So the process ends at each node in the computation graph that represents a weight W. At that point, the sum of the incoming messages to W is partial L partial W, which is the gradient we need. So weight sharing, as used in convolution neural networks, is handled by treating each shared weight as a single node with multiple outgoing arcs in the computation graph. So during backpropagation, this results in multiple incoming gradient messages. So it's clear then that the process of backpropagation is that computational cost is linear in the number of nodes in the computational graph. Okay, it's same as forward propagation. Not only that, but because the node types are typically fixed when the network is designed, all of the gradient computation can be prepared in symbolic form in advance and compiled into a very efficient code for each node in the graph. Now, one drawback of backpropagation is that it requires storing most of the intermediate values that were computed during forward propagation in order to calculate gradients in the backward path. So this means that the total memory cost of training the network will be proportional to the number of units in the entire network. So that's really the biggest problem here, is that you have to store all this intermediate information until you reach the weight W. Thus, even if the network itself is represented only implicitly by propagation code instead of a data structure, all of the intermediate results of that propagation code have to be stored explicitly somewhere. So that's the biggest drawdown of backpropagation, but still, essentially, all neural networks today are trained using some type of backpropagation algorithm. Okay, next we will talk about batch normalization, and this is important to improve convergence characteristics of the network. Okay, see you in the next video.